asteroid. X to the 2/3 plus y to the 2/3 equals 5 at the 0.81. Right, so I mean we could graph it easily on Desmos. It's already, the graph's already provided for you, but I mean if you want a kind of fully functional graph, you can pop it in there. Alright, so you get that nice graph. You can plot 8,1. So it's ready to rock and roll when we come up with the tangent line equation to see if it's valid. Alright, so derivative. We need to compute the derivative using implicit differentiation. Alright, so power rule. Right, in each case, but when you apply the power rule for the y term, we're just going to slap on a dy dx. So 2/3 x to the negative 1/3 plus 2/3 y to the negative 1/3 times dy dx. All right, so a lot more streamlined as we go forward. All right, so now it's just a matter of getting dy dx alone. You could actually divide out the 2/3 from every term. It'll just cancel away. Yeah, that's kind of cool. The presence of the 0 on the right-hand side allows that to happen. Right, so the next line here would be x to the negative 1/3 plus y to the negative 1/3, poor quality 3, dy dx is equal to 0. I want, again, I'm trying to get dy dx alone. We took a little baby step to toward getting there, but we do need to get rid of that x to the negative 1/3. So I have y to the negative 1/3 dy dx. If I subtract the x to the negative 1/3 from both sides, 0 minus x to the negative 1/3 would be negative x to the negative 1/3. And then we're just going to divide out the y to the negative 1/3. So dy dx would be equal to negative x to the negative 1/3 divided by y to the negative 1/3. Now, you could clean this up further. You have some negative exponents. You could put it in radical form if you want. I mean, I don't know the benefit of that because we're going to do a numerical substitution anyway. So you might as well just leave it as is, because if you're going to go to the calculator, I mean, if you're going to do it in your head, then you might want to clean it up a little bit. But if you're just going to the calculator to compute it, then this is an appropriate form. So I'll put what the simplified form would be, just so you have it. But you know, most of the time you're not going to need it. All right. So the negative exponents allow movement from one part of the fraction to the other. So this is the same as saying negative y to the 1/3 over x to the 1/3. All right. When you raise a number to a fractional exponent, the numerator of the fraction is the power, the denominator is the root. All right. So this is the same as saying y is being raised to the first power, and you're also taking the cube root of that. So the same as saying negative the cube root of y. And on the bottom it would be positive the cube root of y. Oh, sorry, x. All right. So just so you have it. Anyway, to find the slope of the tangent line, dy dx would need to be evaluated such that xy is equal to 8,1. All right. If you have it in this form, it's kind of nice, because that's saying the cube root of 1 negated over the cube root of 8. But if you put it in the calculator, it'll do it just as well. So, all right. So in this case, cube root of, well, in every case, cube root of 1 is 1, cube root of 8 is 2. So negative 1/2 would be my slope. All right. So again, if you needed to pop it into Desmos, you could. So what I would do is just crunch it numerically. I wouldn't try to do anything too fancy. So negative x to the negative 1/3. So the x value is 8. So in a fraction, negative, well, it's negative on the outside, so negative 8 raised to the negative 1/3 over 1 to the negative 1/3. It says negative 0.5, but we know that that's the same as saying negative 1/2. Right, so it doesn't look very nice, but I mean the answer looks beautiful, but the computation doesn't look very nice, but it's easy enough. All right, now they want the equation of the tangent line. All right, we'll find the equation of the tangent line to the asteroid. So y equals m times x minus x sub 1 plus y sub 1. So we have the x sub 1, y sub 1. We have the m, so we're good to go. So y would be equal to negative 1/2 x minus 8 plus 1. So then I could just pop that into my graph. So y equals negative 1/2 x minus 8 plus 1. All right, up plus 1. There we go. And so at the coordinate 8, 1, if I bring it in a little closer, that does look like a tangent. All right, it looks like it's coming to that point, 8, 1, touching it one time, and then just getting out of there. All right, so we got the job done. And it took a fair amount of writing, but you know, it's not terrible. The next one, we have some product rule involved. I mean, there's always the option whenever you're dealing with any kind of equation to try to get it into explicit form. But in this one, it says using implicit differentiation, so you don't have a choice. But if you did have a choice, my first thought would be try to solve this for y in terms of x. All right, you actually could pretty easily. You know, you just add the y to both sides, factor it out, and lo and behold, you'll have your explicit form. But we're doing it implicitly, so you know, you just buckle up, right? The first derivative is not that bad. It's the second derivative where you kind of earn your keep. So we have x squared times y. X squared y is a product, right, which means that we're using the product rule. All right, so the first function, we got our two functions here, x squared and y, or factors. The first times the derivative of the second. So the derivative of the y would be 1 times dy dx because it's a y variable. So dy dx. Plus the second, y, times the derivative of the first, which is just a 2x. On the right-hand side, the 1 goes away, 1 is constant. Derivative of a constant is equal to 0. All right. The negative y, we could look at that as negative y to the first. That would be negative 1y to the 0th. All right, so that's just negative 1. But because it's a y derivative, we multiply by dy dx. All right. So now I have to consolidate those dy dx's. So, I mean, it's helpful to kind of clean it up a little bit, but in previous problems, it was really necessary. In this case, you know, I would just rewrite it so that the 2x and the y are more consolidated, 2xy. I don't think that's a necessary step. But what I would do here is just swap these two parts of the equation. All right? You know, using appropriate algebraic operations, we make the swap. You know, we're subtracting and adding to both sides, but those two should be in the reverse positions, right? Because I want the dy dx on the left, I want the thing without the dy dx on the right. All right, so x squared dy dx plus 1 dy dx, or just dy dx, is equal to negative 2xy. All right, so then we have the common factor of dy dx, the GCF. X squared plus 1 would be left over after we factor that out. And getting dy dx alone is just a matter of dividing both sides by x squared plus 1. All right, so dy dx would be equal to negative 2xy over x squared plus 1. All right, so that's our first derivative. So you know you're in for a little bit of a ride for the second derivative because it took that much work to get the first derivative. All right, so we start off with this. Just kind of, oh, that's weird. Kind of chuck it over here. Now I'm going to take the derivative, d dx, of both sides of this equation. All right, on the left-hand side, that just simplifies, that's the easy part, d squared y over dx squared. On the right, we actually have to find the derivative. And the way we would do that is using quotient rule, but part of that quotient rule would be implicit differentiation. And also product rule. All right, so got a fair amount of work ahead of us. So we'll start off with the quotient rule. And, you know, like for better or for worse, my preferred approach to doing this is by using the notation. So it's kind of like a placeholder. When I go through the quotient rule, I'll use the notation d dx to indicate that I intend to take a derivative, but I won't actually take the derivative in that moment, all right, out of fear that it's going to get so complicated that I'm going to make a mistake. All right, but that's a me thing. All right, if you think you can find the derivative on the fly, then by all means go for it. All right, so we have a low d high minus high d low. So the low is x squared plus 1 d high minus high d low over the denominator squared, and away we go. All right, so the derivative part for the x squared plus 1, that's going to be easy. That you could have done on the fly. It's this one that we got to take some time to do. All right, so you know, it gets messy, and I find myself having to shrink it down pretty frequently, but it is what it is. It is what it is. All right, so just kind of off on the side here, I'm going to take my d dx of negative 2xy. I'm going to look at that as a product of two factors, one of which is the 2x, the negative 2x, and the other is the y. All right, so that means product rule. Two factors in the product. Oh, a little too thick. So we're looking at the first, negative 2x, times the derivative of the second. All right, by now you start developing a little bit of, I'll call it muscle memory, but it's really, I mean, sometimes you get questions right in math because you've seen them before. You know, like when you see x squared minus 4, you figure it out when you're factoring to x plus 2x minus 2, not because you're following the process for factoring it, but because you've done that problem 30 times. 30 times would be an underestimate. But you've done it a ton of times before, so you just know it. All right? 6 times 8 is 48. I'm not sitting there being like, all right, I got 6, another 6 is 12, another 6 is 18, and so on until you get to, oh, it's 8. No, it's 6 times 8 is 48 just because. All right? It's always been that. It always will be that. All right? So now when I get to a point here where I'm taking the derivative of y with respect to x, this y term, we've already done it like 5 times, and every time it's been dy dx. So now you just start remembering that. So plus the second function which is y, times the derivative of the first, which is just going to be a negative 2. And it's another situation where why? Because that's what it was the last 7 times we did it. You know. So first times the derivative of the second plus the second times the derivative of the first. If I'm going to be able to squeeze this into that quotient rule, it's probably a good idea to clean this up, even if it's just a little bit. Just do a little bit of simplifying. So negative 2x. I'll need my dy dx minus 2y. Now again, that dy dx is a known value. We figured that out already. So I'm going to take that and make a substitution. And so this is actually the derivative of the negative 2xy. That's what needs to go into the green. All right, so this whole thing here. All right, I'll just redraw that. So all of this is going in for the green. So then, it's really just copy-paste job, but I'll rewrite it this time. So d2y dx squared. It's kind of weird, and I don't like it, but I understand why they do it. The notation for the second derivative is pretty much what I wrote here, d2y over dx squared. They don't use the parentheses, even though it actually should be dx as a quantity squared. So you could actually go either way with the notation. This is actually technically correct. Alternatively, it really should be d squared x squared. But for whatever reason, I guess for simplicity's sake, they let you just get away with writing it without the parentheses. Who are they? The whole calculus universe. So x squared plus 1 times all of this. All right, so times, I'm just gonna actually multiply these two things. I want to be able to write less. So 4x squared y over x squared plus 1 minus 2y. Right? So that's something, and all of that is a contained quantity, so I got to get a bracket around that. Or another set of parentheses, but you know, I like to distinguish the two. So then going back to this part over here, I see I have 2 negatives, so let's make that a positive. So plus 2xy. And then I just need the derivative with respect to x of x squared plus 1. That's easy enough. That's just 2x. Right? So times 2x. And if you wanted to consolidate on the fly, you could do that too, but I think that's probably enough consolidating. All over x squared plus 1 squared. That was a good one. It's a fun problem, you know. You don't want your entire future to be dependent on your ability to get this question 100% correct. But you know, it's kind of like a crossword puzzle where if you're doing it for fun, you know, it's like, you know, it's a good beefy math problem, you know. So yeah, that's that. Now, I just wanted to talk to you a little bit about logarithmic differentiation. There's really no new skills involved in it. It'll seem like there is, or are, but it's really not that complicated. So as long as you know your derivative rules, and as long as you know the rules of logarithms, the basic ones, you know, the power rule for logs, product and quotient rule for logs, then this stuff it should be pretty straightforward. So I'll do 2 examples. The first one you look at and you say, well, isn't that just 2x? And I say, yeah, but we're going to do it using logarithmic differentiation. The benefit of log differentiation is it allows us to take products and represent them as sums. It allows us to take exponents and represent them as coefficients. And it allows us to take quotients and represent them as differences. All right? Finding the derivative of two expressions being added versus the derivative of two expressions being multiplied, it's an apples and oranges comparison. One's way easier than the other. All right? So I chose y equals x squared as the first example because we know what the answer is supposed to be, and so we could verify that the technique works before we do something more complicated. All right? Now, the very first step is to introduce a logarithm. So we take the natural log of both sides of the equation. And that allows us to take any exponent and make it a coefficient. All right? So we'd have the natural log of y is equal to 2 ln x. So as long as you know your derivative rules for natural logs, you're fine. Right? It's information you got to know, just in case you don't. All right, so if you have the derivative with respect to x of the natural log of some function, it's the derivative of that function divided by the function itself. Right? So, I mean, it's a pretty complicated way of writing it, but it's the catch-all way. Right? So when we are looking for the derivative of the natural log of y, we could call that y prime over y. When we're looking for the derivative of the natural log of x, because 2 is just a constant multiplier, comes along for the ride, that's going to be x prime over x. All right? So if we know that y prime is the same as saying dy dx, and x prime is the same as saying dx dx, then that makes the x prime irrelevant because that's going to cancel. So what we're getting here is dy dx over y is equal to 2 over x. Then we just have to solve for dy dx. And that's multiplying both sides by y. So dy dx is equal to 2y over x. All right. And you're like, well, that's not 2x. Well, it actually is. It's sort of in disguise. All right? Because the y here is equal to x squared. So if we know y is equal to x squared, then we can make that substitution 2x squared over x, which simplifies down to 2x. All right. But you could also leave it in terms of the variable y. But it's kind of like, well, if we wanted to verify that the technique works, we would definitely want to go that extra step. Right? So the benefit of this approach is not for things like polynomial functions. I mean, you just saw here that this is basically like driving from New York to New Jersey via Canada. You know, like we definitely took the long way around. Right? So we don't want to do that. All right. We want to use it strategically in situations where it's like, whoa, this is going to be a nightmare if I have to do a chain rule question that has product in it, a product rule, quotient rule, like it's got all the trimmings. Log differentiation will simplify that so that you don't have to use all those different rules. All right. So for example, in number 2, if I say instead of y equals all that stuff, I say the natural log of y is equal to all the natural log of all that stuff. Now this denominator I'm going to write it as a fractional exponent because that's what we do. All right. You could do a couple of things here. One approach is a little bit easier than the other. You could use the quotient rule for logarithms to break this up, but you could also introduce a negative exponent. All right, so we could say ln of x squared plus 1 to the negative 1/2 and use the power rule for logarithms to make that negative exponent into a coefficient. Doesn't matter. Why does it do that? It doesn't matter that it was negative. I don't know why I emphasize that. Just that it's an exponent. All right. So then ln of y would be equal to negative 1/2 ln x squared plus 1. All right, so using the natural log approach, we were able to clean this up pretty nicely. Ln of y has the derivative of y prime over y. Now, because we know y prime is the same as dy dx, we don't actually have to rewrite it in terms of dy dx. Ultimately, we want to solve this for y prime. All right? Whether it's in the form of dy dx or not, it doesn't make a difference. We just want to figure out what the derivative is using whatever notation makes sense. All right? On the right-hand side, I have my negative 1/2 multiplied by the derivative of this, which is 2x, over the expression itself. If I want to get y prime alone, I just multiply both sides by the y. All right. Can't help it but to simplify this because I see a 1/2 and a 2. So this is the same as saying negative x over x squared plus 1 multiplied by y. And since we know that y is equal to the 1 over the square root of x squared plus 1, we have our derivative. All right. But it's still, I think, probably one of those situations where you're like, I would do it a different way. Probably use the chain rule. Yeah, wouldn't be that bad. But then you look at number 3. And you're like, I'm less inclined to want to do it using ordinary methods. But then you get to number 4, where you actually can't do it using methods that we've already learned. All right, so that's the rub there, because you can't just look at this and say, well, it's an optional topic. You got to look at it and say, well, it can be convenient under certain circumstances, but it's going to be necessary under other circumstances. All right, so in the case of number 4, so I'll skip number 3 so you could try that one on your own or in small groups. But in the case of number 4, you look at it and say, well, it's not an exponential function, so I can't use my exponential rules. It's not a power function, so I can't use my power rule. It's not a product. It's not a quotient. So what would you do? You would use log differentiation. So I take the natural log of both sides. The benefit of a logarithm is that it allows us to release an exponent. So that exponent is now a coefficient, or in this case, a factor. So ln of y would be x times the natural log of x. We do a little product rule on the right-hand side, but on the left-hand side, that's that muscle memory I was talking about before. The last 2 times we did this, ln of y had a derivative of y prime over y, so why would it be different this time? On the right-hand side, fix that. The first function times the derivative of the second plus the second function times the derivative of the first. And my ultimate goal here is to get y alone, or I'm sorry, y prime alone. Too thick. So I would multiply both sides here by y. So I'm looking at x times 1 over x, which is just 1, plus ln of x, multiplied by y, which is x to the x. Ah. Yeah, I think I got into such a groove I let the computer time out.